All right, you guys, we're going to be talking about exponential functions. And wow, if these aren't relevant with the way the virus grew this summer, I don't know what is. So, an exponential function is something that grows exponentially. And what that means is that it doesn't grow linearly. Like linear has a rate of change. So, if we're looking at comparisons, okay, a line has a constant rate of change. So, if you decide, say, you want to bake a dozen cookies, and it takes 1 cup of flour for a dozen cookies, okay, you would be able to know. Sorry, let me see. Let me try this again. You would be able to know that for 1 dozen, you would need 1 cup, right? And if you wanted 2 dozen, then it would be 2 cups. In other words, as one increases, as one is increasing, the other one is increasing. They're both increasing at some rate, okay? That's line. That's um, a linear equation. These are going to be exponential. So the thing about exponential equations is that they increase exponentially. And what that means is, like, for example, if you have, well, first of all, how to recognize them. You can recognize them. And by the way, I'm putting notes here that belong probably on a separate page, but I'm just doing them here and then erasing them. So copy them from here and then we'll work. But the idea is that it's an exponential function. So basically, it's going to be a number, a base raised to the x. So the exponent, we call them exponential equations because look, the variable x, the variable is in the exponent position. Exponent, guys. Okay, position. So in other words, like if you had y is equal to 2 to the x, what that's saying is that you are increasing by a base of 2. So for example, if, oh my God, I'm so sorry. I can't seem to draw a line. Nope, that isn't it either. Wow, it's been a little while, huh? So let's try that. Okay. Oh, so much fun. Thank you. Thank you, thing. Okay, let's try this again. Okay. So if you had, for example, x and y, okay, and let's just see if I can get this kind of right. Okay, so y is equal to 2 to the x. So let's say you plugged in, let's plug in a 0. Okay, so you would go 2 to the 0 power, which is 1. And then you plugged in a 1. That's 2 to the first power, or 2. Let's say you plugged in a 2 for x. That's 2 squared is 4. So look, here we doubled it. Okay, we multiplied it by 2. Again, so you're thinking, oh, I got this. Okay, we multiplied this by 2, that by 2. Okay, by 2. All right, and then look what happens when we start going 2, 3. That's 2 to the third, which is 8. So we doubled that, okay? But every time we're doubling it, okay? And you have absolutely no idea how quickly this goes. It literally starts like this, you guys. It starts low, and then it goes zoom. And I guess you do have an idea because if any of you ever looked at a COVID graph, I mean, if we're going to talk about relevance, right? You can actually see, and I'm going to go do that right now. Let me go ahead and put this pen away for a second. Check it out, okay? I should be able to go here. I asked it to do my whole computer, so hopefully you're not just getting blanks, okay? So if you do worldometer, Corona update right here, okay? I don't know if you guys have checked out this website. I was watching it all summer long. So let's say, so 47 million cases worldwide. Get away. And okay, so here's the interesting thing. Here's some graphs show the graph. So this is, okay, this is worldwide. So 1.2 deaths. Let's go by this. Okay. Let's go USA. So we are almost at 10 million cases total. But you can go like this and you can see the graph right here. Not that graph. This is an interesting graph. It's kind of a weird one. Where's the graph? I haven't been on this site for a little bit, but they typically have for a while there, they had some amazing math stuff. It was amazing. It was so great. And then they took it off. But let's see. Projections? Sorry. Okay. So this is kind of linear if you're looking at this. Okay. It kind of looks like it's increasing at the rate of change. Same rate. And then all of a sudden, this would be exponential right here. When it starts increasing more. That would be, this is exponential right here. Heck yeah, right here. It's like do. Okay. And then we went down and then now, okay, that's exponential. Okay, exponential is like this crazy growth where it just keeps doubling. And you can actually look at these points on this graph. Check it out. Observed, 38, 81. Let's see if it doubles in the next point. 101, not quite, 128, so we're going up by 30. And then all of a sudden, it goes from like 260 going up to 300. So we're not going up quite by a power of 2 yet, like by twice as much going up. I don't know what percentage. We could actually figure this out, though. We could actually grab a couple of these points and figure out this exponential equation, which is kind of cool, y'all. All right, so let's get back to this. Sorry, I digress. All right, so exponential equations are where there's exponents in the variable. So the very first thing you're going to learn how to do is simply plug in this stuff, okay? That's all you have to do. So if you're going to plug in a -1, that's going to be 1/3 to the -1. And you guys should know that 1/3 to the -1 means 1 over 1/3, or remember, it just flips it. So it becomes 3, okay? Because 1 over 1 divided by, remember to divide fractions, I could change 1 to a fraction. And to divide fractions means to multiply by the reciprocal, okay? Hope you remember your fraction work. All right, then we get 1/3 to the 0 power, and that's 1. So this is 3, that's 1. And you will see a pattern. It's just not a linear pattern, okay? 1/3 to the first power is 1/3. So you get 1/3. 1/3 squared is 1/9, because it's 1/3 times 1/3. Now you can see what's happening here. We're multiplying by 1/3 every single time. So this is going to be 1/27, because 1/3 to the third is equal to 1/3 times 1/3 times 1/3, or 1/27, okay? So in the beginning, it's pretty easy. All you have to learn to do is to plug in the exponent and solve it. Now, don't forget that you know how to do that. I'm always amazed that people just don't use tables. Use tables. Okay, next problem. Graph the exponential function. All right, you guys, this could be really ugly, but it's not. It's kind of amazing how quick and nice it is. Okay, because remember, we know the pattern. It's just going to go like this. Well, let's try this again. Right? It's going to go very quickly up. All right. So you only need a few points to do this. It says 5. All right. And so let's do 5. Okay. Usually we only graph 2, but you guys aren't at that level yet because you don't understand the shape yet. So they're making you do 5. But here are the points. So what points should you pick? Well, nobody's going to be picky. Let's do x, g of x, because that's what they called y here, right? Okay, let's always pick 0. Let's pick 1. Let's pick 2. Okay, so if you plug in 0, you get 5/2 to the 0 power, which equals 1. 5/2 to the first power, which is 5 halves, you guys, but because we're graphing it, let's change it to a decimal, 2.5. Okay, 5 halves to the second power is going to be 25 fourths. 25 fourths, which is, if you divide it, you're going to get 4 goes into 25, not is 6 and 1/4, right? 6.25. Okay, then, okay, so you can see what we're getting so far. And you can do 3 and 4. Okay, a lot of times you actually can't do these. 3 and 4 would be way too high. So they're going to be giving you, like here, they're giving you a fraction that's equal to 2.5. So it's a little bit slower. Anyway, let's see. So 3 would be, what's 3? 3 would be 5 halves cubed, which is 125 over 8, which is, and this is where it's nice to have a calculator, but if you have a calculator handy, do it. If not, you can always do this. It's just a little tedious because look, I mean, who wants to do this by hand? And 5/8. Okay, yeah, I would highly recommend you could do that by wait, 5/8. I thought that's at 5/3. I was like, no, you can't do that. Okay, 16 and 5/8. So you could change that. Is it 16 or 15? I can't even read my own dang writing. Okay, 45. Oh, it's 15. It's 15 and 5/8, which I shouldn't have done that. We should change it to decimal. So we could possibly, it's a little bit over half, right? 5/8 is a little bit over half. I could have just added a 0 like this, and I would have gotten 8 goes into 56 times. Is that right? 48? Yeah, 48 to, and who cares? At this point, you're not going to graph anything more than a tenth. No way. So 15.6. And then the last one is 5 halves. So have your calculators handy, you guys. 5 to the fourth is 5 times 5 times 5 times 5, 125 times 5, which is, I believe, 650. Why do you keep doing that, you dumb? Okay, and 2 to the fourth is 16. So you could do that. You get the idea. And then what you do, and I'm not going to do it just because it doesn't make sense. Okay, you guys are going to have to do it on Alex anyway. And then you're going to have to just graph it. So, wow, I'm having trouble drawing straight lines, you guys. I don't have my, ooh, hello. I don't have my board. I don't have my board in like the right position or the right angle. Somehow I'm not quite there. I moved it and now I don't know where I'm at. All right, so let's say you have this, okay, and you got X going here. This is your X, this is your G of X, right? Okay, we're gonna graph it. So X is gonna go from 0, here's -1, 0, 1, 2, 3, 4. That's what we plugged in. 0 is 1. 0 is almost always gonna be 1 unless we add something to it, okay? 1 is 2.5. So you go here, 2.5. Now, when you guys enter them into into Alex, you'll be able to do this a lot easier than me. 2 is 6.25, so obviously it would be up here, and you can see what's happening. I actually like to do -1/2 to plug it in, because then you get 5 halves to the -1/2, which is, okay, remember the negative will flip it. So you get 2/5 squared, which is 4/25, which is about 1/4. If you're trying to like look at it, or actually it's more close to 1/6. 4 goes into 25 6 times. Yeah, 1/6. Wait, 4, yeah, 1/6. 25, yeah, 1/6. 1/6. Okay, which means that it's kind of like low here, right here. Really tiny. So you get the idea that it comes really, really, really close to the x-axis here. Sorry, I can't quite draw it perfect. And then it starts going up, and it goes up, and then it goes, oh gosh, sorry guys, I'm trying. And then it goes up. All right, that's the idea of an exponential function, and that's how you graph it. Just plug it in. Don't forget that you know how to plug it in. Plug it in, plug it in. Now look at this one. How is this different? So take a look at the master formula, you guys. A and B are going to be integers of some sort, okay, or not even integers. They're going to be rational numbers. So here's the thing. You've got A, you've got B. First, we just had B of X. That's the base. What is the A going to do? Now, you can go over to Desmos and play. I highly encourage you to do that. Let's go over there. Let's go to Desmos. Check it out. You can check it out and see what the heck it does. What if I do y equals, let's go 2 to the x, okay? Get down. Let's see, y equals 2 to the x. Oh, we'll do that. You have to hit that so that you can get the exponent, 2 to the x. Okay, check it out. And then play with it. Like put a number in front of here. What if I did 5 times? Ooh, wait. 5 times 2 to the x. Look what happened. Instead of going through 0, 1, it goes through 0, 5. Okay? And you can play with it and see. And you can also do it in the next line. So y equals 2 to the x. Okay? And you can see what happened. Well, if it goes 5 times faster, guess what? We're making it go zooming up even faster. This is like rocket ship status. Okay? All right. So now all you have to do is plug it in. Okay, so that's all we're going to do. I'm going to plug it in. So you make a table or you just plug it in like this. Let's do g of -1. Okay, let's go all the way to -1. So 1/3, actually that's very typical of what I do. I typically do like -1. So that's 1/3 times 1/5, which is 1/15, which is basically so close to the x-axis you can't even graph it. But you guys can, because you can put it into you can put it into the point grapher, whatever, the coordinate grapher on Alex. And then we'll go of 0. So what's going to happen? You're going to get 1/3 times 5 to the 0 power. Well, 5 to the 0 is 1. Remember, any number to the 0 power is 1. So that's going to be 0, 1/3. So all we're doing is plugging it in. So g of 1 is 1/3 times 5 to the first power. That's 5/3, or if you want, that's 1.66, I believe. So about 1.7. About 1.7. Okay, g of 2 is equal to 1/3 times 5 squared, which is 25 divided by 3, which is 8 and 1/3. 8 times 3 is 24, and there's 1 left over. And then last, g of 3, which is 1/3 times 5 to the third power, which is 125 over 3. Okay, because remember, this 1/3 is not part of the exponent. The base is the only thing that gets pulled to the exponent, and this is going to be 441. You're not going to be able to graph that unless they pulled it back. So if you get something way off here, you might have to pull in something in between, like 1.5. Okay, but that's definitely a calculator problem, because you would have to put 1/3 times 5 to the, put that little caret, you know which one, the little button with the caret, or whatever the exponent, and then you would have to put to the 1.5. Yeah? Okay, so just so you know. Okay. All right, that's it. Just plug in the points, move on. All right, below is the graph of 1/2 x. Now, oh my gosh, what happened here? Why are we going down instead of going up? Okay, everything we've done so far, take a look. The base has been 5. This is 2.5 because it's 5/2. It looks like a fraction, but it's greater than 1. It is a fraction, but it's greater than 1. It's 2.5. Okay, and this was 1/3. Okay, and I didn't graph it. We didn't graph this one. I just found, so we didn't talk about this one. Okay, I did say that they go like this, but this is called exponential increase because it is increasing. There is also an exponential decrease. And a really cool example of something that decreases exponentially would be coffee, the heat of a coffee cup. It's really, really high. The temperature is really high, and then over time, it comes down really quick, and then it kind of just stays and goes, okay, and it takes a while. That would be an exponential decrease. Okay, and some things function this way. Some things decrease exponentially. Well, how can you tell an exponential decrease from an increase? Okay, and the key is right here. If the base, okay, if b is greater than 1, it's increasing. If b is less than 1, it's going to be decreasing. Okay, because basically, if you think about fractions, you guys, if you multiply a fraction by a fraction, you get a fraction if it's less than 1, right? If you take 1/2 of 1/2, that's actually equal to 1/4, and we just got smaller. And if you take 1/2 of 1/4, you get 1/8, and that's even smaller than 1/4. You see it? So we are getting progressively exponentially smaller. Okay, that's just showing you how that works, but that's actually, hang on, let me do this. Okay. All right, so here we go. What we're going to do, it says below is the graph of 1/2 x. Translate it to become the graph of 1/2 to the x minus 4 plus 3. All right, so this is basically following the same pattern you've learned already. This moves the graph up and down. And look at how weird it is, but it's still the same. That's going to move it left and right. And in this case, because it's plus 4, it goes the opposite direction. Remember, we want to get it to a 0. So it's -4. So we're going to move this -4. So you grab this one point that you have and you move it -4 here, but it's also going to go up 3. Right there. Wait, 1, 2, 3. That is the new point. So it moved 4 to the left and up 3. That's what these directions told you to do. Okay, and then what you want to do from there is try to mimic the graph. And the easiest way to do that is because, okay, do you see how this is 1 up from the x-axis here? So what you want to do is, you're not translating the x-axis. You are kind of giving it a new point of reference. This is almost like it was the x-axis. It's almost like we're mimicking it. So we're drawing that there, and then now you can bring it down and make it come really close. I'm sure you won't have to do this by hand. I didn't do that. Sorry. I don't understand how this, I think it has to do with the fact that I'm recording. I think the recording screws up everything because it doesn't do this when I'm not recording. Okay, here we go. Coming down through there. Okay, so the idea is that we just reference everything. You moved it 4 to the left, 3 up, and then you move your reference axis, the x-axis, up, and you draw a dotted line. So you get an idea of where it is. Okay, and then you're going to just draw the graph. Okay, next. About that, let's try this again. Okay, it says the graph of an exponential function is shown in the figure. The horizontal asymptote. Okay, so the asymptote is where it would never hit. So this is called an asymptote. An asymptote is basically an imaginary line that the function will never reach, but will keep getting closer and closer. So you can approach an asymptote, but you'll never touch an asymptote. So, sorry, I went the wrong direction. Here we go. A little bit to go forward, we shall see. Okay, there it is. Okay, the graph of an exponential function is shown. The horizontal asymptote is shown as a dashed line. Fill in the range in the domain. Again, remember, domain is x. Okay, it's what x can be. It's where you run your domain. You think of it as flat land, okay? Range is the y, okay? So take a look at the domain. Basically, the way you want to ask this is there any value for x you can't find a value for y? So I go here, look, oh, I can find a value, I can find a value. No matter where I walk on x, there's nothing stopping me. No, I'm not hitting anything as I walk, as I travel along this x-axis. I am free to move, okay? I'm free to move. There's nothing stopping me. So that's going to be from negative infinity to positive infinity. So what does it want? Inequalities. So you're going to put x is between, okay, negative infinity and positive infinity. Okay, that is, or do they put all reals? Okay, sorry. They can put all reals. All reals. Okay. Range, on the other hand, check it out. You're going to hit this asymptote. You'll never be on this side of the asymptote. There will be nothing on this side because the asymptote keeps everything from crossing. This graph is like, it is moving along, but it cannot drop down, okay? So the range is from this line, and it's not equal to that line. So y is going to be greater than 1, because it can't reach 1, and goes all the, actually that's it. Y is greater than 1. That's all you need, okay? And you could actually put it this way. Y is greater than 1. Those two say the same things, okay? Y is greater than 1, eating the Y, yeah? Okay, next. Okay, use the Alex calculator to evaluate each expression. Okay, and basically this is, can you plug in decimals? And that is it. Literally, that's it. That's all it's asking you. It's asking you to recognize that there's an exponential button that works here. So not even this one. Let's see. Let's say we're going to go to Decimal Scientific, and I'm hoping that you can see this. Decimal Scientific. If you can't, what you're looking for is that button that you can, it's the button, this button here, this A to the B. Okay, so you can put any value, like if you wanted to put 2.14, which is a decimal, to a decimal, okay, 5.3, which is weird, right? The answer is right here. It can do it. Your calculator can do it with this little magical button right here of A to the B. Okay, that's what that's about, just helping you learn how to plug things in to your calculator, and that's it. Moving on. Okay, now we're getting to a real world situation. And at first these seem kind of hard, but they aren't. Okay, they aren't. If you write down the key, okay, every exponential function is going to come like this. Okay, let's say, first of all, I don't know what P and T are, but I can tell you right now that P depends on T. T is what we're plugging in, and P is what we're going to come out, what's going to come out. So P, it turns out, is the price. Okay, and it says T is the number of years from today. That's really important. The number of years from today. Okay, because sometimes they'll tell you it's the number of years from 1990, and you better pay attention to that. Okay, so P of T is equal to, and then here's what's going to happen. Do you remember that A? Actually, let me put it here. F of X is equal to A times B to the X. Okay, well, look, what if X were 0? Okay, let's say we start and the time is 0. So X equals 0, right? That would be A times B to the 0. What's B to the 0? 1. In other words, that is just going to be A. So here's the thing. A is what we start with. It's kind of like the B in a line. A is our starting point, okay? That's what we're going to start with. B is the base, and the X is the exponent, okay? So if you have something that is going to be increasing, okay, that's what we're going to be looking at, is the B, and the A is where we're going to start with. So it says the rate of inflation is 3.4% per year, okay? The future price in dollars of a certain item can be modeled by the following exponential function, which is t number of years. I wonder if this really works, you guys. Like if a price, like a price of a carton of eggs, like if I, how much would it be in like 5 years? I could put t to this t is equal to 5 and see what it would cost. I remember when I was little and cars were a certain price, and I remember thinking, there's no way they're ever going to be 50,000. And here they are. Okay, find the current price of an item and the price 10 years from today. Find the current price of the item and the price 10 years from today. So the current price is going to be right now, which is time is 0. Okay, so the current price is really just this. Okay, but the thing is that you could actually plug it in. Nobody's stopping you from doing the math. 1.034, okay, to the 0 power. And this is going to be 1, and it's just going to be 2,500. Then you want to do P of 10. So you're going to plug in 2,500 times 1.034 to the 10th, okay? And you would plug that into your calculator. Okay, so something that costs 2,500 today. Guess what costs 2,500 today? 1.034 times to the power of 10. I'm trying to think, what would cost 2,500 today? I don't think if I bought anything for $2,500. It's not really something I do. Okay, 2,500. Okay, and then we're going to go, and I don't need a comma, but I think it doesn't care. Okay, to the, oh, no, not to the, sorry, backspace, times, oh, and you must put a times, guys, times 1.034, and it knows that base. Okay, so I'm going to do that to the 10th power. Okay, what did I do wrong? Okay, it says I did something wrong. Oops, I did something wrong. Let me see. Maybe in decimals I can't put, oh yeah, can't put a comma. Don't put commas, that's stupid. All right, so something that costs $2,500 today in 10 years is going to cost almost $3,500. Wow, that's a lot. That's a big increase. Okay, and yet it's really only increasing 3.4%. That means it goes up 3 cents on the dollar every year. Okay. By the way, do you see how that's a 1? Okay. Make sure you don't forget the 1, because what that does, this little 1 here makes you, it basically is making this 2,500 get added to this quantity. It's because look, you could do 2,500 times 1 plus 0.0, yeah, to the 10th power. Okay, so we want to make sure that you include that 1 there. Okay, moving on. All right. Again, use the Alex calculator. Again, okay, so here's the thing. We are now going to be using something called E. It's called Euler's number, and it's spelled like this. Euler was this genius mathematician, and he discovered this number, and he named it after himself, and it's called E. And banks use it every day to calculate your interest and calculate things. We use it all the time. What it is, I can't explain to you what it is because it makes more sense in calculus, but you know how pi always exists? Like you have a circle, and if you take the distance around that circle and you divide it by the diameter, you always get 3.14. Okay, that's just pi. All ancient civilizations had discovered something close to pi. Like basically they realized that if you take the circumference and divide it by the diameter, you get something close to 3. Okay, Euler discovered this natural exponential number, and I can't explain it to you. All I need you to know is it is on the calculator. You can find it. Look at it. It is always, hang on. It is always, ooh, okay, it's not here. Wait, let's see. Is it on functions? Yes, here it is. Do you see it? E to the x. It is a natural base E. Okay, we are going to be dealing with E a lot I'm not asking you to understand it. You guys, it's one of the hardest things to actually get kids to understand, and it's just not worth it. I'm not, it really isn't worth it at all. So all you need to know is it is a number that occurs naturally, and it is a natural exponent, and it is actually equal to 2.7812, I don't know, and it goes on to infinity. Okay? This is Euler's number. Okay? We just use E because it serves as a good natural base. Again, you won't understand it, just trust me. Just use the button on the calculator that says E. It says round your answers to the nearest thousandth. Thousandth is 3 digits, okay? Do not round any intermediate computation. So really all you're going to do is enter 350 times, and then you're going to hit e to the b or whatever it is. Okay, and then you are going to put e to the, and then put a parentheses, negative 0.75. And then it'll be equals, it's fine. Okay, it's just teaching you that the E button exists. That's what that problem is about. All right, and then it wants you to plug in things with using this. So here, it says the number of milligrams D of H. So we know that D depends on H. So it's the number of milligrams of a drug. So D stands for drug, milligrams of drug. Like they don't tell you that, but they are. It's a milligrams of drug, okay? And H is the number of hours after injection. Okay, this kind of stuff is actually really important because look, they have to know this stuff, especially if you poisoned yourself or you've taken something really bad kind of thing. It's really high in the blood, and then over time it's going to decrease. But it takes a while to get out of your bloodstream, you guys, and sometimes they use that to your advantage. Like if you take something like, like a regulatory medicine, like something for one of your like organs or something that you take, maybe thyroid or whatever, they are banking on how much is in your blood. So you take the first dose and maybe it goes down, and then you take another dose in order to try to keep your blood at some kind of constant level. It's going to try to do that. They know about this. Okay, so here we go. Is modeled by that function. Okay. Find the amount of the drug after 4 hours and after 8 hours. So all you have to do is plug in the H. That is it. They're just asking you to find D of 4. So to find that, you plug in 20 times, find the E button, and plug in negative 0.45 times 4. And then go back and change that to 8. That is all. Okay, nearest hundredth. Pay attention to that, okay? That's it. It's a lot of plug and play. Eventually this stuff is going to feel very easy to you guys. It's just a lot of plugging in. And I think that is it. It is. Okay, that's day 1 of exponential functions.